Special thanks tonight to Lam Research for sponsoring the program. They're a terrific partner and one of the world's leading companies in the semiconductor industry. So thank you to Lam Research. So for a very brief moment, I'd like you to all focus your attention on the screen, and we'll take a little video from Lam. Well, thank you to Lam Research, and thanks for that. For those who didn't hear this afternoon, I'm going to say it again if you were here this afternoon, that it's the likes of Lam and all the work that's been done in the semiconductor industry that allows this current meme of software is eating the world to play out. I happened to be at an event a long time ago where Gordon Moore spoke, and he followed someone who made a statement of that ilk, and he smiled as he is wont to do, and when he got on the stage, and he said, yeah, software may be eating the world, but it's got to run on something. And so tonight's that special night to celebrate semiconductors. With that, I'd like to introduce the IEEE president from 2017, President and CEO Karen Bartleson, and she'd like to say a few words about the Shockley Semiconductor Laboratory dedication that took place earlier today. And with that, the plaque associated with Moore's Law. So please join me in welcoming Karen to the stage.
Thank you, Daniel. Good evening, everyone. Thank you all for attending and being part of this very special program. I am honored to be here to dedicate IEEE's latest milestone award to Gordon Moore and his well-known prediction known as Moore's Law. IEEE is the world's largest technical professional society, whose core purpose is to foster technological innovation and excellence for the benefit of humanity. Our 430,000 members in over 160 countries define technology's state-of-the-art, develop industry standards, and leverage the power of technology to advance the human condition. The IEEE Milestone Program is funded by donations to the IEEE Foundation and is administered by the IEEE History Center. It recognizes great moments throughout our world's long history of technical innovation. Tonight's milestone distinguishes Gordon Moore's prediction in 1965, while he was at Fairchild Semiconductor, that the number of transistors in an integrated circuit would increase exponentially over time, doubling roughly every year and a half, while cost per function decreased, which guided the industry's contributions to advances in electronics and computing for more than 50 years. Earlier today, we dedicated an IEEE milestone at the site of the original Shockley Semiconductor Laboratory, celebrating its historical significance as the first company in the area to research and manufacture silicon-based semiconductors. This led to the growth of the semiconductor industry and truly the foundation of Silicon Valley. It is my privilege to recognize these two pioneering events and the people behind them. They serve as landmarks in the progress of technology and the advancement of civilization. In fact, Congresswoman Zoe Lofgren, who represents the 19th District of California, which is based in San Jose, the capital of Silicon Valley, provided 2 proclamations also commending these IEEE milestone events. I want to thank all the organizers, including those from the IEEE Santa Clara Valley section and the Computer History Museum, for all their efforts. At this time, it is my pleasure to introduce tonight's moderator, David Brock. David is the director of the museum's Center for Software History, as well as a historian of technology. He has written extensively about the history of semiconductor electronics, most recently co-authoring a biography titled Moore's Law: The Life of Gordon Moore, Silicon Valley's Quiet Revolutionary. Please join me in welcoming David to the stage.
Thank you. Yeah, thanks. Well, thank you very much, Karen, for that kind introduction. And, you know, coming after Karen and her excellent remarks about Gordon Moore and Moore's Law, you'll notice a pattern of repetition here, but I can promise, you know, I wrote it before. So to begin. It's hard to overstate the profound consequences of silicon electronics across the past half-century. The unceasing exponential changes in silicon microchips and the mind-bendingly small transistors they contain in equally boggling numbers has made these tiny digital switches the objects most made by humanity. The cost of digital electronics and computing fell by the billionfold. The capability of computing expanded by equal amounts. With these changes, digital electronics and computing have suffused every corner of our lives. Through the inaudible hum from the sextillions of invisible switches, we have added a new layer of reality to the old, an electronic reality into which many of us are connected more than we are not. Today, the story of silicon electronics and all it has afforded has started a new chapter, turning a page from certainty to uncertainty. We're lucky to be joined tonight by 2 individuals who are writing this new chapter to help us understand what may lie ahead. But let's begin by turning to Gordon Moore, a pioneer of silicon electronics.
In 1965, I was asked to write an article predicting what would happen in the next 10 years in the electronic component industry.
Moore predicted that the number of transistors on a microchip would regularly double for the foreseeable future.
So I said, okay, in the next 10 years, it's going to continue to double every year. Pretty wild extrapolation. And one of my colleagues dubbed this Moore's Law.
His prediction came true. Year after year, electronics have become astonishingly more powerful and dramatically cheaper.
By making things smaller, everything gets better. The electronics get faster, they get much cheaper, the power consumption can go down, and the complexity of the systems that are possible goes up dramatically, as does the reliability.
Moore's Law became the guiding principle for electronics over more than 50 years. It has driven that industry and the digital age.
The participants in the industry now recognize unless they stay at least on that curve, they fall behind. So everybody really sees the need to stay right up here to the front if they're going to make devices that are really leading edge.
Today, the transistors on microchips have parts that are just a few atoms thick. They can't get much smaller. Could this atomic limit mean the end of Moore's Law?
We clearly have a barrier that's insurpassable that's coming up here before too long. In fact, several years ago, I thought it would be in this decade that we really reached the limit. That still makes sense to me, although I hope I'm wrong.
Well, earlier I saw Federico Fagin and Ted Hoff, who may have recognized one of those early die shots in that film. It had a 4 and 2 zeros and a 4. Let me introduce tonight's guests. Mark Bohr is Senior Fellow and Director of Process Architecture and Integration at Intel. He's currently directing early process development activities for Intel's 5-nanometer generation silicon technology. Mark joined Intel in 1978 and is the author of dozens of patents and papers. Bill Chappell is the director of DARPA's Microsystems Technology Office and its new $1.5 billion Electronics Resurgence Initiative. Before joining DARPA, Bill served as a professor of electrical engineering at Purdue. So please join me in welcoming Bill and Mark.
Thank you so much.
Thank you. Thanks.
David.
Well, I know that Gordon Moore is a bit of a tough act to follow, but I did want to ask each of you to give us each of your big picture perspectives on the dynamics behind microelectronics and computing across the last 50 years. Anyone care to take a stab at that first?
Something small.
Yeah, just a little light softball.
I'll take a stab.
Thanks.
You know, I think what's really amazing is it's an exponential for 53 years. I love actually talking to people from other fields. It's like in vogue to compare yourself to Moore's Law, right? So gene sequences is falling faster than Moore's Law. And I'm like, tell me in 53 years where you guys are at, right? Because this is actually an exponential that's gone on way longer than he even thought, as he mentioned, more than really it ever should have, right? It's a miracle, right, that you can have a one-way trade space where everything gets better, right, if you go in one direction. Engineering is supposed to be this complex series of trade-offs, right? And we caught magic, and that magic has led us to the world that we live in today.
Mark, any thoughts?
Some people may think of Moore's Law as a law of physics, and it's not. Others, maybe more correctly, may think of it as a law of economics, and it's close to being a law of economics. But I think it's a law of human ambition, human cleverness, and human competitiveness. We all want to have the next great thing a little bit sooner, a little bit better than the other guy.
Mark, could you say a few words, if you could, about one feature of Moore's Law, or what is described by it, has been this kind of regularity, almost a metronome in terms of this incredible development every few years. Could you give us a little insight into what produces that beat?
Well, again, I think it goes back to the competitiveness nature of our industry and the engineers that are a part of it. They want to have something a little bit better, a little bit sooner than the other guy. For a while there, it took about 3 years. The cadence between technologies was about 3 years. That still delivered the doubling that Gordon talked about by both a combination of smaller transistors, but also larger die sizes. So there was a period in our industry where die sizes were continually growing. So that's why you could get a doubling every 2 years, even though you're developing a technology every 3 years. Mm-hmm. But then the real competitive part of our industry came in the mid-1990s when Intel and other companies started to develop technologies at a faster pace, a 2-year pace. And that was about as fast as we could all do it, to develop a technology, develop a chip, get it up to good yields and good volume. But now I'll admit that pace is being challenged as our technologies are getting much more complex than anything Gordon ever dreamed of.
I have a question for you, Bill, but maybe to give somebody watching who, is not a devotee of silicon electronics like many of the people in the room with us this evening, to give, when you're explaining it to someone, how do you give people a sense for how small the features are on today's chips and the abundance of these switches on today's chips? Well, maybe that's maybe a question for either of you.
Well, I use two types of metrics. One is you can fit hundreds of these transistors across a single human red blood cell. That's one measure. But the other is we make chips that are the size of a thumbnail that have billions of transistors on them. So that, I think, indicates just how small they've become. And in some of our structures, with a good enough microscope, electron microscope, you can almost count the atoms across the transistor.
I think another way to look at it, modern microchip has 20 to 30 kilometers of wire. So you take 20 to 30 kilometers of wire, cut it into 10 to 100 micron sections, and then place them so strategically that you have nanosecond events that are all timed so that everything has to work, right? So it's not just the number, right, which is kind of the byproduct of Moore's cramming more into a small space. It's actually the complexity that has led to, and the ability to actually strategically place the wires in a way that actually the society's banking on that it works every time.
Right, because it's not just a matter of making these fantastically small switches by the billion. You have to connect them together in order to have them work. And so you're saying that if you take all of that patterned metal,
stretch them out. Yeah.
How long is it?
20 to 30 kilometers. You probably have an even longer estimate.
I don't have that number in my head, but that does not sound unreasonable.
So go from here to San Francisco, and like every 100 microns, chop that up and rearrange them.
I think a good point you brought up is it's not just transistors, it's the wires, the interconnects as well. Sometimes our interconnect engineers at Intel feel a little bit underappreciated, but more than half the cost of making a microprocessor chip is the wires connecting those billions of transistors.
Yeah, Gordon Moore I've heard him joke that it's actually an interconnect technology. It's 22 or whatever layers of wires atop these transistors. Another joke that I've heard him made is that Moore's law is kind of this perpetual violation of Murphy's law, which I thought is kind of funny. And with that, could you share with people your thoughts on, okay, they're impossibly small and crazy numbers. What are the implications of that? So what are the consequences for that in the life of somebody listening to us tonight?
I think you're asking, what do modern microprocessor, modern integrated circuits do for people?
Sure.
Hopefully, all of us are old enough to remember when a personal computer, you plugged into the wall and it sat on your desk at home, and now you've got something much more powerful, much more useful in your hand. So that's what it does. Or some people think a Google search is effortless. You just type in something. They don't realize that those signals zoom off to some data center in some remote location and find the answer you want and send it back to you. And so you're using a lot of computers every day.
I'd go even bigger picture and say it's the foundation of life as we know it right now. We live in a digitally influenced society to a level we can't go back. And Moore's law is really the foundation which that society has been built, which is a double-edged sword. It means as we make this progress and try to run faster, you can't make flaws. We now have the burden of actually being the basis of the foundation of society. So there is not a field, right, like biology, like you name a science, it has been propelled by as much by Moore's law as just the knowledge that they built through their own domain.
I think that many people will be familiar with Intel. It's possible that fewer people may be familiar with DARPA, although as a historian of technology, it seems like the air. But perhaps, Bill, you could explain to people briefly what DARPA is and how does Moore's law connect into DARPA's world?
Yep. Our job is simple. We're here to eliminate strategic surprise for the country. We were created literally weeks after the launch of Sputnik, and with a pretty simple mandate of don't let that ever happen again. So pretty broad range, right? And so microelectronics is a big portion of that, right? As I said, it's the foundation of society. So where's surprise going to come from? It's in domains like microelectronics. So one way to avoid strategic surprise is to create it, right? So we've been, we hope at the tip of the spear doing things that industry's not. Out ahead, we try to look 10 to 15 years ahead and do things that aren't quite market-driven yet, right? So just examples of what we funded, 193 nanometer lithography was something that the rest of the world was kind of chasing X-ray lithography, and we kind of went a different tack, and that became an industry standard about 10 years after we initially demonstrated it at Lincoln Laboratories. The FinFET at Berkeley was something that was a really bad idea until it wasn't. Right? And so we're trying to do sort of that exploratory work out ahead of, and then we let go. And I think one of the things about the cadence that you talked about earlier is fascinating. Is I actually think every 2 years, or that direct cadence, is really a symbol of a society that's functioning. Right? It's a government that doesn't get possessive of an invention, right? That you can do something like the FinFET and then walk away from it and say, this is good for society. It's academia that's partnered with industry, which is partnered with government, and you've got this three-legged stool that's actually working together to propel the community, and that's very rare. It's actually, I think, unique in the electronics domain that we've had that open research cycle where there hasn't been possessiveness to try to maintain it either within the government or try to limit sort of the broad international exploration of that technology.
Let's talk a little bit about, to help me and everybody else make sense of discussions we're reading and hearing about the end of Moore's Law. It's over, it's not over. We hear various opinions. You could hear my kind of fudge at the beginning by saying uncertainty. I'd love to hear you both speak to that conversation. What's the biggest misunderstanding? What's going on in this conversation?
So I joined Intel in 1978, and only a few years later, in the early 1980s, I was going to conferences and hearing some senior voices in our industry predicting the end of Moore's Law already in the early 1980s. Now they had some valid, or I'll call them semi-valid, reasons to extrapolate the end of Moore's Law. One of them was transistor gate oxide thickness, which when you scale has to get thinner and thinner. And you can start to count the silicon atoms and realize by the year 2000 we'll run out of silicon atoms. The gate oxide will be too thin. Thus, that will be the end of Moore's Law. So that was a reasonable prediction at the time, but it didn't account for cleverness when Intel and others in our industry invented high K and metal gate transistors, which allowed us to continue scaling even though the SiO2 gate dielectric had stopped scaling. And the other example is patterning or photolithography. We use a certain wavelength of light to pattern the features on the wafer. In the early days of our industry, the feature size was large compared to the wavelength of light that we were using. And the industry was still learning how to scale the wavelength to enable ever smaller feature sizes, going from 365 nanometers to 248 nanometers to 193 nanometers. But that pace of scaling the wavelength was much slower than the pace of scaling the minimum feature size. So it was reasonable to predict Moore's Law will end because we can't pattern features small enough. But again, I think some of those early experts underestimated engineer cleverness in our industry, where we invented techniques like double patterning, then quad patterning, phase shift masks, optical proximity correction. So today, we're still using 193 nanometer wavelength of light, but we're patterning feature sizes down around 10 nanometers. So my physics professor told me that was impossible.
Bill. One of the reasons there's misconceptions or just arguments as to kind of where we are, and you mentioned this earlier, is really an economic argument that he was making, right? That he called it cramming more electronics into integrated circuits, and that you should do that until a particular system function is minimized. So those are actually the words that he used, and the cost of the particular system function is minimized. And so it depends who you are, right? It depends what your cost structure is, right? Mm-hmm. From the DoD's perspective, right, if you actually include NRE, then we've actually struggled with the spiraling costs for over a decade now. If you're Intel and you're making X number of components, then it's still going. But so it really depends on what you include in the definition of a system function. Right? And you know, he really wasn't talking about NRE, but I do think that that's the type of how do you interpret those words, and does it include you know, which part of the cycle, and is it just about is scaling going to continue, or is scaling going to continue in a way that makes economic sense to continue that scaling? And I think that is what we're facing right now, is more economic challenges. Right? I think we will continue to invent. The real question is, will we continue to invent in a vector that continues that one-way trade space? Faster, you know, lower power, lower cost, right? All of the different dimensions that it scales down, that is the magic which Moore's Law predicted.
But we could, I mean, certainly, you know, the technology that Intel is using today, 10 nanometers, you know, features on the chip are measured in terms of 10 nanometers, which is what, 10 billionths of a meter. You're working on 5, smaller. Yeah. Certainly we can't get to 0 or -1, you know, so there's that progression.
Well, you're forgetting it's a log scale, so there is no way.
Just asymptotically to 0. But you get the sense of my question. Something, I suppose, will shift, and this is looking at it in a different, looking at the problem from a different vantage point.
Well, I think the physics express themselves in cost, right, in the business cycle. So I think that's, you know, goes back to his original discussion, right? And he was actually admiring that packaging was so expensive that transistors were free. That's actually the basis of his bathtub curve. And so it was really the economics which was driving that discussion. And if that ceases, it doesn't mean progress stops. It just means the one-way trade space is no longer alive.
Right. Mark.
So I think it's true that eventually you can fool physics for only so long, and eventually you can't scale a transistor, you know, at least by any means we know, below the size of an atom, or maybe even below the size of a handful of atoms. But I think there's still a lot of innovation, a lot of architecture changes that can happen to continue scaling. And the one example I like to give is the human brain. Maybe it's not quite as fast as most computers, but it can do a lot of things that computers can't today. And it does it with components, neurons, that are much larger than a transistor, and does it at a power level about 25 watts, lower than anything that we can make in silicon. So, you know, nature hasn't revealed all the secrets yet, but I think there are still ways to create ever better computing systems.
Yeah. And I would agree with that. I think whatever the dynamic is in terms of the cost, I think progress is made. Actually, it's, I think, much more interesting, right, at where we're at right now, right? I mean, as an engineer, you want to create something tomorrow that doesn't exist today. You want a challenge. And this is actually a really interesting time to be an engineer in this space. It sort of gets misinterpreted. The end of Moore's Law is a sort of a morose, you know, description of where we're at. It's actually, you know, it's a better time to be an electrical engineer than ever, I would say.
Well, maybe we could switch gears a little bit and talk about current activities and current efforts to build this future of electronics. And perhaps we could begin with you, Mark. And could you describe some of the scale and scope of Intel's efforts to push forward this development of silicon electronics?
Boy, that's an interesting question I didn't expect, but I think I've got an interesting answer. You know, when I first joined Intel, here in Mountain View, I worked in Mountain View Fab 1, the process development team I was a part of had 2 process engineers, me and my boss, and a technician and a device engineer. Today, a process development team is at least 100 times bigger. And the fab is 100 times, maybe 1,000 times more expensive than the original building. So it's a much bigger business, and it requires not just smart engineers, but an organization that knows how to organize that work in an effective way, leading towards a productive product.
Could you, before we turn to Bill's description of the efforts afforded by DARPA, could you talk about how How is Intel approaching maybe the need to explore these other dimensions, look at other possible routes in terms of when you're talking about the massive scale of changing this process technology. So how are you kind of both doing the same and exploring what could be the different thing that you're doing later?
Well, I work for a company in an organization that in our heart and soul realizes every 2 or 3 years we've got to come out with a compelling new technology, at least process technology on my side. And maybe at some time, at some points in our history, we only had to simply follow Dennard scaling. Just scale horizontal dimensions, vertical dimensions, supply voltage, and voila, you'll have a good technology. At other times, we recognized years in advance that we've got a big roadblock coming. The gate oxide won't scale, the lithography won't scale. So we really scratched our heads, years ahead, started to explore other ideas to enable scaling that didn't use traditional scaling methods. And some of the inventions we came up with included strained silicon transistors, high-K metal gate transistors, and of course the FinFET. Not our invention, but we learned how to adopt that and use it, develop it to be effective for our types of products.
Bill, could you give us an overview of the parts of DARPA that you're involved with that are kind of exploring this space?
Yeah, so we just kicked off what we think is a fairly major initiative, which we call the Electronics Resurgence Initiative, which is $1.5 billion in the basic of electronics over the next 5 years, about $300 million per year. And honestly, it's really an ode to Gordon Moore. Right? When we looked at kind of where we're at and trying to avoid strategic surprise and try to project in the future, we were shocked at kind of the words of wisdom that he had in that initial paper. So I actually want to kind of, if you would, show that paper, because I just think this is unbelievable. It really is like drop your pencil level of shock when you read his initial words. So, all right, everybody knows this, or maybe many people in this audience will recognize the bathtub curves, right? This is, if packaging is the driver, I'm going to put as many chips in as small space as possible until yield hits me and get yield on one side and cost on the other, and you find a bathtub at the bottom of the bathtub, and there you go. And it's the basis of Moore's Law. This is page 2, 3-page paper, right? So this is like very simple. You can see his language, cramming more components into integrated circuits. This is not, professor speak for trying to be too fancy here. I can say that as an ex-professor. This is page 3. So we called our new initiative the page 3 initiative, our latest round of investments, page 3, because Moore's Law, even though he deserves the credit that he gets, right? It was an observation, and the community made Moore's Law what it is, right? On page 3, he gives just as much insight. So let me show you here, right? First, he says the total cost of making a particular system function must be minimized. He gave us the boundary condition, right, that really describes where I think we are today, actually. It's this sort of this inflection where cost is creeping up, right? It's harder and harder, bigger fabs, bigger teams, bigger design teams, bigger verification costs, bigger software development costs, right? Everything in the market is spiraling in terms of higher cost. He's saying here a particular system function must be minimized. Okay, so we're in inflection. He then goes on to say, right, what are you going to do about it? He says, let's design things where you can amortize the design, right? So I can design one thing and then use it in different architectures. He then goes on to say, perhaps I can translate automatically from a high-level description into a silicon realization. He's calling for a revolution in CAD or EDA. Right? In 1965, he's staring at 50 transistors, right? And he's projecting, hey, I want to do something like a silicon compiler, something from a high-level representation down into the physics. And then he also then says it may prove to be more economical to build large systems out of smaller functions. He's calling for the chiplet revolution, right, or this heterogeneous integration that we're starting to see sort of cascade through our industry. So in 1965, he kind of nailed it, right? He described like 4 DARPA programs that we're actually doing. And it's humbling when you realize that, you remember that $100 million program we just kicked off? He told us to do it in 1965. I finally went back and read and went, okay, so that's where I dropped my pencil. So what is he really describing here? If you actually go to the very bottom, he's talking about hyper-specialization, aggressive specialization, right? That through rapid design and or assembly, you can get lots of different variants. And you're starting to see that today, from the TPU to the GPU to the plethora of solutions that Intel has to some of the neuromorphic that they're looking at. You're starting to see this proliferation out from just one massive design into smaller designs that cater for different applications. So we kicked off a program we call CHIPS, right? It would say, as he said, it may prove more economical to build large systems out of smaller functions. So what if we just blow it up, take the last 53 years of cramming, and then let's actually separate that, right? And what does that world look like? And it's actually a fascinating world. It's what he described, and now I don't have to beat silicon. I can be a materials developer, and I can add my special flavor in one of these blocks, and I don't have to actually, compete with Mark. I never want to compete with Mark. They know what they're doing. They've got 53 years of head start in silicon development. Maybe we can do an exotic material, but it's only good for one thing, but let's have it only do that one thing, right? Or I don't have to redesign my SerDes block that I just spent, millions of dollars developing at one node, even though it doesn't necessarily get better as you scale. What if we can actually just make that a chiplet, a physical chiplet, and integrate that? So this is work we're doing with Intel. Intel is actually the base provider of their FPGA. Using their EMIB process, we're actually creating a national standard that is now open source and license free for the community, so that they can start looking at how do you build these chiplets and add that into the mix of computing. But it also then gets more interesting, because now, as I don't have to do everything in one new process node, if I've got a small fab, maybe I can do something really exotic. I can explore the third dimension. This is work we're doing with Stanford and MIT, carbon nanotubes, working with ReRAM, vertically integrating memory and logic, smashing that all together. And when you have a memory wall problem, putting that all together, you can see that actually a 90 nanometer node with this built on top is actually better than a 5 nanometer node. That's the analysis. We haven't proven that, but that's what the simulations would show. You also then can start looking at exotic materials, right? We're working with Global Foundries on some of their magnetic memories, but you can also look at the work we're doing with Applied Materials on next generation MOT transistor, or MOT memories. And now you don't have to compete with silicon entirely. I can start using some of the exotic material properties, just do one function better. We're doing deep learning inside of the memory structure on its own. And so, whether that's the right idea or not, it doesn't really matter. It's a different world where you start to be able to invent on much smaller chunks, right? And now a startup doesn't have to beat the 8,000 engineering years it takes to create a GPU.
Yeah.
They can potentially just add an accelerator into the mix. And I think this is the type of thing that kickstarts the electronics industry over again.
Mark, I think you also had some slides that we were going to look at.
But before we get to them,
yes.
let me make one other comment about Gordon Moore's 1965 paper. If you read the whole paper, towards the end, he starts to predict what these integrated circuits will be useful for.
Yeah.
One of his predictions in that 1965 paper was personal computers.
Yeah.
About 20 years before it
Yeah.
became a reality.
Right.
So,
Can I show something?
pretty sharp guy.
Let me see if we can go back here. I wanted to show that paper because it's so cool.
Yeah.
Let me go backwards real quick. I know I'm off script here. Look at that cartoon. It's hard to see here. That is a cartoon of someone selling personal, or handy home computers is what the title says. And it's right next to someone selling cosmetics.
Yeah.
Right? So you've got cosmetics sitting next to handy home computers in 1965.
Yeah.
He also, in his very first sentence, or first paragraph, describes a wristwatch, right, that basically is the Apple Watch today.
Yeah.
Right? And then the last paragraph, and this is really where I kind of went, this is just kind of weird. He is describing the impact on millimeter wave systems, or microwave systems, of the integration, right, for what he called linear systems, really RF systems. So he's describing RF millimeter wave phased arrays, right? Which is really the heart of 5G, is the battle that we're fighting right now in 5G. So in 1965, I don't know exactly how he did it, but that's where I think his true wisdom. Yeah, there's Moore's law. It was a simple observation on page 2. Actually, you turn the page, you get even more insight.
Maybe it's a personality test, but I'm drawn to Day of Reckoning
right.
at the top.
Yeah, no, it's this morose. It really is like, it's like any engineer, like a little cynical, right, about how the challenges that we face, but with huge insight underneath it.
Mark.
Yeah. So I'm an engineer. I like graphs. That's how I speak. So this is what Intel and our industry has been doing for the last 50 years of scaling. Back in 1965, when Gordon wrote his first paper, the typical minimum feature size was more than 10 microns. And now we're down around 10 nanometers, so 3 orders of magnitude over those 50 years. That's quite a long record. This graph also makes a point I think I made earlier, that during the 1970s and 1980s, our industry was developing a new technology about every 3 years, and each technology would provide about a doubling in transistor density. Then you say, but what about why is it over 3 years? Well, it's because, as I mentioned, they're also increasing chip sizes. So transistor counts were doubling every 2 years or so, even if the technology was scaling every 3 years. But then, in the mid-1990s, we all, I think, got the competitive fever, and let's get our process out 6 months before the other guy. And admittedly, that was also in the what I will call the golden era of Dennard scaling, where you could follow a simple formula, or at least it seems simple by today's perspective, of scaling horizontal dimensions and vertical dimensions, and still achieve great results in terms of density, performance, and active power. So we followed that as an industry for several years. And maybe another factor in that acceleration is that's probably about the time our industry had some consolidation going on. So you had maybe fewer players, but you had stronger players who could accelerate the pace this way. And now when we get to this era, 2015, 2018, admittedly, things are slowing down again, maybe closer to a 3-year cadence, just because the technologies are so much more complex, so many masking steps, so many process steps. Takes longer just to get a wafer through the entire fab. So that's stretching out the technology nodes maybe closer to 3 years than 2 years. But that doesn't mean Moore's law is necessarily slowing down, because even though the cadence may be slowing, we're taking bigger steps in terms of improving density. So that kind of shows up on this graph here. Here I'm plotting the transistor density for Intel's logic technology using a very quantitative metric, using some common logic cells, where you can measure the area of the cells and how many transistors are in each cell, and you can calculate from that transistor density in units of million transistors per square millimeter. So as you can see in this graph, our 14 nanometer technology took a little bit longer than our 22 did, and our 10 nanometers taking a bit longer than our 14. But these technologies have done more than doubling transistor density. So they're still roughly on that trend line of doubling transistor density every 2 years. And now our 10 nanometer technology has a capability of about 100 million transistors in a square millimeter. So that's on a human scale, that's a lot of transistors. But as I also mentioned earlier, simple, again, maybe in retrospect it seemed simple, but Dennard scaling kind of ran out of steam around the year 2000, when the gate oxide was the silicon dioxide gate oxide was about as thin as it could ever get without having excessive leakage power. So we were forced to come up with novel inventions, off the roadmap inventions, to enable transistors to continue to get smaller and yet also deliver good performance and lower active power and low leakage power. In 2003, we came up with strained silicon, a way of improving transistor performance without having to scale the gate oxide thickness. In 2007, high K and metal gates, so we replaced the silicon dioxide gate insulator with a hafnium-based gate insulator that had much better leakage properties. And then in 2011, FinFET technologies, so converted from a planar transistor to a kind of a three-dimensional transistor that had much better short channel characteristics. So I think our industry is now in this mode where we have to continually come up with innovations in both transistor materials and structures to continue scaling.
Thank you. You know, looking particularly at one of Bill's slides with the chiplets, I think you called them, reminded me of right at the very beginning of Intel, Gordon Moore pursued what he has called his Goldilocks strategy. There were two different process technologies, bipolar, silicon gate MOS, for making the chips. So there was a competition there between those two flavors of technologies, but also what he called multi-chip.
Right.
Make easier to make parts and put them together in a chip. And our one of our museum fellows this year, Dov Froman, made a multi-chip memory. It worked, but Gordon Moore said, "I'm sorry, but I think the economics are favoring, you know, making it as one big chip." Yep. And it's interesting to see that come back, but in a different way. And what I was getting was a theme from both of you in a way of hybrid technologies or a heterogeneous approach where it wouldn't just be, where it would be certainly silicon chips, but working in tandem with other things. Do you think that's fair?
I think that's a very important point that can't be stressed enough. If you look back 10, 20 years ago, and again, maybe the golden era or the best part of Dennard scaling, it was all about CMOS transistors. You can take a CMOS transistor, maybe little tweaks, but you could do anything with a CMOS transistor, logic, memory. But I think those days are now over, where we need much more specialized devices, transistors optimized for high-performance logic, others for memory, other for analog. So we need to develop more heterogeneous technologies, and they don't always fit economically on one piece of silicon. So multi-chip solutions are probably the way of the future.
I think the thing that's happening right now, which I don't think is very disputable, is massive specialization at the architecture level.
Yeah.
Right? And I think yesterday, NVIDIA announced their GPU doing real-time ray tracing. 10-year goal. Everyone thought it'd be 10 years away. They announced it yesterday, and it's because they have a deep learning accelerator next to a ray tracing accelerator, and they're working together. That type of accelerator blocks that are added in to create this specialized architecture it's often running TPU, GPU. That race is ongoing. The question is, how do you get new materials into that mix, or do new materials get into that mix? And I think that's still a question. I think we're banking on that it will, because that's what we're investing in, as we showed, but I still think that's actually a game yet to be played out. There's different places across the stack where you can do that aggressive specialization, and I'm hoping that it goes all the way down to the materials level, but I think that's still an active debate.
Let's help people who don't know what you mean by architecture. We have these chips, we have this phenomenal abundance of these switches, we have these kilometers of wires interconnecting them all. The architecture is really the design of what you're making with that abundance. Is that an okay simplification?
It is, right? So, and a recent, vintage, though it's been around for a long time, but more aggressive uses of accelerator blocks, so IP blocks that are specific for a specific domain. So, we at ERI, our kickoff last month, John Hennessy came and espoused the whole domain-specific architectures where, for example, their TPU that Google's now using, right, is specifically for their machine learning applications. So they're re-architecting specifically for that domain That's happening. The GPU is starting to specialize even further for a variety of, not just graphics, but also machine learning and other domains. The real question is how many domains does it span? How thin do you slice that? Right? Are we living in a world where Budweiser becomes an IPA and a stout and a do we go towards that level of hyper specialization, or do we have just sort of relatively coarse specialization? And then how much of the material development is a part of that?
Mark, how does that architecture question look from Intel?
Well, I am not, I can't claim to be an architecture expert here, but I do have interesting discussions with some of our product designers and architects to learn what interests them and how the process technology may have to change to better meet their needs. Again, I'm not an expert, and my examples here are maybe very simplistic, but whether you design a process and a microprocessor to have one massive, really powerful core, or whether you try to divide it up into many smaller cores, whether you try to have a lot of fast memory really close to the core or not. So there are trade-offs here in terms of cost, complexity, and power, how you architect the system, and of course how you deliver the technology. And that just puts these different architectural options and their need to innovate and improve puts pressure on or challenges on the process team. They'll say, well, we love your logic transistors, but what about your SRAM? We want more of that, or DRAM. We want more memory.
I think your example of the microchip module that he did before is actually a great example. It's been done many times before. The economics didn't work out. I think some of the things that Intel and the rest of the community is coming out with, where your shoreline is such fine bumps that the difference between something on chip and two chips, right, is smaller than ever. You're looking at sub picojoule per bit energy transfer from one chip to the other. So as a designer, you can start to feel like you're designing one single chip, even though it is heterogeneous. And I think that's the hope for why that idea has been around enough, but the density is such that you're actually getting into a very interesting space.
And I think an important point that Bill may be getting at here is that package technology, which maybe used to be thought of as this mundane last thing you do, is now coming to the forefront in terms of being a key enabler for heterogeneous systems. Connect together the different chips that you may need to deliver the best system performance and power.
So in some ways, to reflect back what I'm hearing, for a time the solution was like always make a better, faster, more capable general purpose computer on a chip. That is a kind of the major solution. Now we're moving to, well, let's make a different chip for different problems, but that carries with it all sorts of challenges for how you make it, but also, how on earth do you design a thing with 100 billion parts?
Some people may think, well, disaggregation is the future. Okay, that may be true. Then you have to think of, well, how do I reaggregate them?
Right.
Because you still have to do that. It still has to be an integrated system.
Bill, did you have a thought?
Yeah, well, I was going to say, I have a program manager that joined us who had a small company, Dan Hammerstrom. I actually worked with Intel for years and was at Portland State. He had the world's best neuromorphic chip. It had the most transistors ever put on chip for about a year and a half, and then Intel ran right over him. Right? So he had a year and a half to establish a new chip technology, and that's kind of the double-edged sword of Moore's law, right? Is that with that continual progress, some of those innovations that were great, for their time, you always had this freight train coming, behind you, and so some of the things that we're talking about could thrive more, right, with a little bit longer, a little slower train nipping at your heels. But I still think that having designed a portion of the chip as opposed to the entire chip allows you to innovate fast enough to specialize in the right way.
I wanted to ask a question about partners. How has that landscape of the key partners for your efforts, Mark at Intel, yours, Bill, at DARPA, are we seeing a change in that? Who you work with, who you rely on? What's that look like, the landscape of partnership?
Well, I think with the scale that came with Moore's law, the community is increasingly important, and as the scale got bigger and bigger, the more complexity you have, the more the community relationships have mattered. I think from the research side of things, I will, not just because you're here, I mean, Intel and the government have actually had a very strong relationship. At the electronics level, there's not a lot of controversy on we should partner. And from SRC, where it's a 60-40 government funding 40, industry funding 60, where we fund around 650 graduate students across the country, that's something that we have in the electronics industry that we don't have anywhere else. There is no software version of that. There is no aerospace version of that. That is something that actually Intel and IBM primarily have been the stalwarts of that, with DARPA joining in, and there's other versions of that with NSF. That's unique. That is not something that we should take for granted at all in this field. 650 graduate students. You just told me you had about 2,000 PhDs working at your facility. They have to come from somewhere.
Yeah.
And this is something that has been a partnership from the very beginning. The scale is so big that we can't invent things on our own. First off, we don't. We always empower other people to invent. We have to do that with the commercial world. The government has to tie themselves to the government world and vice versa to do relevant research in this area.
And just the SRC is the Semiconductor Research Corporation,
Yep.
which is this kind of joint venture between the public sector and the private sector in supporting work relevant to semiconductor electronics in the academy.
Yep. The stuff outside of what's in their lab today, right? They're hopefully feeding new ideas for DARPA programs and feeding new ideas to, when they do get stuck, that there's new thoughts on the table.
Mark?
So examples of some of the important external partnerships for Intel. Obviously, the process development team has to work with the tool vendors, the equipment vendors, to make sure they've got the latest etch tool or thin film deposition tool that we need. Our product design teams obviously can't just design a chip and then throw it over the wall to the computer vendors and expect that they'll love it the way it is. So you have to collaborate to make sure it has the right features, the right software compatibility. But maybe the other one that we've already touched on in Bill's discussion here as well, between industry and academia. I mentioned that sometimes certain scaling paths will end and you need some bright new ideas. So sometimes we depend on university researchers to do that very broad investigation of 10 different ideas. And maybe only one will have value, but you still have to explore those 10.
Let's turn now to maybe thinking about this age of perhaps that Bill was describing as an exciting time where things are maybe a little bit more open-ended in what's happening with electronics. And it just strikes me that with Moore's Law, everyone working in microelectronics and computing today has known nothing else than constant, regular, and positive exponential change, which is a very, so I would, do you have any perspectives on how is this community going to or starting to react to living with more uncertainty?
Well, I think on the research side, I think one of the things that Moore's Law did was it created the goalposts or the boundary conditions for the community to go, right? And so things like partnerships sort of formed when finding that next node was good for everybody within the industry.
Yeah.
We had things like Semitech, we had things like consortium that had a specific target. Right. And that sort of group, huddle, right? Actually, as a researcher, I try to avoid it. Right? We try to do personal inspiration-based innovation, but when you know where you're headed, it's actually good to do the huddle, right? And so that allowed us to know, what was good for keeping Moore's Law going was good for the industry. Now that we don't necessarily know which vector you're going to innovate on, it's actually a lot harder. And so, we've responded by doing a series of individual programs, working with Intel directly, working with IBM directly, working with NVIDIA and Qualcomm, right, on specific vectors that where we don't know if they're good ideas yet, right? But you're doing 1,000 flowers blooming to figure out which ones to to harvest. And I think that's a byproduct of this sort of unique time where it's not as obvious where the next leap forward is going to come from.
Mark, what's your thought?
So having a very predictable cadence or a scaling roadmap was certainly very useful for our industry. We knew if we invested in developing a technology, designing a chip, that 2 or 3 years later you'd have something that would work, be profitable, and equipment vendors would know to have their equipment ready, et cetera, et cetera. So that was good, but that type of predictability can also lead to complacency, and that's not good, especially if you're headed towards a brick wall and you don't see the wall or you refuse to see the wall. Yeah. So, luckily in the 1990s, there wasn't complacency about gate oxide scaling, so many companies and universities were doing the early groundwork on high K investigations. Now we're in another maybe period of less certainty, and I hope that will initiate more hard thinking. Well, what other options are there? What other solutions are there?
I would say Moore's Law, just calling it Moore's Law, has a double-edged nature to it. A law is going to happen regardless, right? You can get complacent just by the naming, right? This was blood, sweat, and tears of mostly industry, but also the government resources and academic resources, and that is we just shouldn't ever take that for granted. And so calling it a law was really an observation made into a law by the electrical engineering community, right? So he deserves the credit that he gets, but it's really a community celebration as opposed to just one man who happened to make that observation. So.
Right, an achievement of a gigantic community with spending untold billions over 50 years. I wonder if there's a sense in which people working in microelectronics and semiconductor electronics, their complacency may erode first, and then spread to other areas. Like there could be other areas that depend on microelectronics who don't realize that perhaps this situation is unfolding. Are there efforts to try and communicate this more broadly outside of the semiconductor community, or?
I think, from my perspective, there's been a broad awakening in the importance of semiconductors. To be honest, China's spending $160 billion, right, to create an industry that rivals ours. That gets people's attention, right? And you can kind of see that in the interesting dynamics that are happening at sort of the geopolitical level, for better or worse. But that is, it has gone from, I think we were complacent to, we kicked off a relatively major effort. A lot of attention is happening, for better or worse. It's got, everyone's attention across the people who matter.
Mm-hmm. Mark, do you have a?
Maybe the other form of complacency I worry about is young people, students, who may not be considering engineering as much as I would hope they would, who are always seeing the latest iPhone or cell phone come out and think this is easy. There's some low-paid engineer somewhere in the world who makes this happen. Well, no, it's a very large. Actually, team doesn't cover it either. It's a very large industry, right, and a lot of work by a lot of bright people that is required to make that happen, and that needs to continue to happen here, and hopefully more students will realize that they should be a part of that.
Two sides of that. There's joining engineering, and then what fields within engineering. I think there's no secret that computer science has exploded, right? And there's a lot of momentum there, and you got a lot of departments across the country doubling in size. Electrical engineering is relatively flat. Electrical engineering is less than 1% unemployment across the country right now. That's an amazing number, right? It is still the basis of all of those systems. Now, I think in the last year, it's actually started to flip. I think people have started to recognize that you can make a lot of good at that foundational level. There's 49 different startups in hardware, really AI hardware, but at least it's a start, right, to other hardware plays, over the last year. Mm-hmm. So, historically, computer science, electrical engineering, always, out of phase sinusoids. But over the last decade, it did sort of take off, and I think you're going to see a renormalizing of that.
And I suppose going back to Mark's observation that it's been this competitiveness that has, kind of been a key element of the dynamic in the development of electronics. Perhaps the competition with China, will be productive. Well, thank you very much for answering all of my questions. I need to give the audience questions a turn,
now for
at
the
least
hard
for
questions?
a bit.
Okay. Now for the hard questions? Okay.
Yeah, now for the really good questions. And here's a prime example of a really good one. What role does software play in overcoming limits to Moore's law?
Mind if I take?
I haven't a clue.
Oh, thank you.
Me neither, but I'm paid to answer regardless. So, no, I actually think if you really buy into this hyper-specialization world, the biggest barrier to that world is the software stack. I can specialize the hardware all I want. I'm just making metal. It has to be usable metal. And if you look at the Trail of Tears, even DARPA research, right? If you hyper-specialize too much and don't pay attention to that software stack, you create an unusable system. So actually half of what we're funding under the Electronics Research Initiative is at the software layer on how you actually smooth the path from new hardware to the use of that hardware. So it's critically important. A lot of people will say, well, what if we just write more efficient software? And there's a lot, we've kind of been bloated. Mark has spoiled us. We can kind of write inefficient code. It's okay because, the chip's going to make up for it over time. You can squeeze that and you will get benefit. You're not going to catch an exponential. You can't replace an exponential just with eking out the software benefits that gain. And that's why this is so hard. If we really need to catch another exponential, it is really difficult to figure out where that is, but you're not going to do that just to the software. I think software-hardware co-design is incredibly important, but I think you're going to get some benefits at the software level. You're going to need the hardware to really propel you towards that exponential curve.
Mark, are you sure that you don't have?
Well, the only comment I can add that maybe have any value is that you can have, a very modest piece of hardware and great software, and that's not a good combo. You can have the opposite. You have great hardware and not so good software. So the two really do need to be co-optimized. Both industries need to work together to make it a truly great product or result.
Another good question, asking you each to speak to the topic of neurocomputing. I think in this sense of both kind of inspiration from the human brain, maybe for electronics, as Mark touched on, but also, interconnections or interfaces of the silicon or the microelectronics world with the brain.
Well, I think the question or the point might be that neuromorphic computing or non-von Neumann computing, if those are the right terms, there's much more interest in that today because think about it, not all computing functions need to be precise to 10 digits. You just may need a close answer, and maybe neuromorphic computing can do it much more power efficiently. Again, 25 watts.
Bill, do you have some thoughts on that?
It's incredibly interesting. We had a relatively major program called Synapse, and we explored that over the last decade. It was a great program, great research. It's still sort of in that research domain. Again, it goes back to sort of the prevalence of Moore's law and some of those very unique things like analog computing, like neuromorphic computing. It really struggles to find room to breathe when everything is advancing so quick behind it. So I think still very interesting research, and we're still continuing to do it. But very few of our systems that are actually fielded are utilizing that type of technique at this point.
Here's a question that I'll let you be the judge if it's a good one or not, because I don't understand it. Could you talk about the implications of memory-centric computing? Is that?
So
is
if
that-
you, yes,
Could you tell
absolutely.
us what that means and then answer the question?
Yeah, so Moore's Law really spoke to the processing. Processing got better. You know, you invent in one direction, you find flaws in others. And I think, you know, one of the major barriers for many of our algorithms is that where the data resides and where you want to process it, they're not in the same location. You have the memory wall. So one obvious answer is move the processing into the memory. So one thing it is exciting, what we're demonstrating is memory-side analog computing, where you're using the actual memory structures as weights and then using the bus as the summing algorithm. So you can do a dot product as an example. Hyper efficient when you actually have the memory as part of the computational infrastructure. And so whether it's just locating functions sort of underneath the stack where you have memory just happen to be located there, that's also very interesting. And then sort of that more exotic approach of actually using the memory cells as part of the computation is, I'm optimistic on that. And there's some startups that have hit the field recently, kind of really trying to make a go of it. And so I think that's one of the solution spaces. And actually, if you look at one of those blocks I used in that chips example, right? You won't do general compute that way. But if I have, for example, a dot product, you know, where I want, or say, a deep learning algorithm or convolution, that's a type of thing that you could put in one of those blocks where you're using the eccentricities of the material or the memory structure to really, you know, get 1,000 or 10,000x benefits.
Wow. Mark, do you have thoughts on this question?
I think Bill knows much more about this than I do. I cannot expand on it.
I'll paraphrase this next question. I guess it goes back to our theme of heterogeneity or hybridity in the future. And this one is asking really about optical or photonic processors and devices. Do either of you have views on the future for that, where we're using, you know, light instead of electrical charge?
So we've poked around for years. At least in the short term, or maybe even say the foreseeable future, much of the processing is going to be done electronically. I think there's really interesting ideas in terms of like circuit switching, all in optics. So you can, you know, so relatively simple but ultra fast switching techniques where you don't have to go from optical, electrical, back to optical. But if you're doing, you know, relatively complex structure logic, CMOS has had that 53-year head start. And whenever you try to completely, you know, go beyond silicon and just completely replace it, it's a really large mountain to climb. So having certain functions done in the optics, I think, is happening. We're doing things like correlations. Right? You're doing correlators inside of the optical fiber and inside of the optical structures. That works really, really well. But we try to expand that to many different stages and increase the complexity. The devices are just very large, right? So it's not very efficient. So it has to be incredibly low latency, right? Or some other reason to do very specific functions in the optics. And that's where I think it'll stay for a long time. Having said that, integrated photonics, I think, is going to be a big part of our advancement, right? And just carrying information where it needs to go all the way to the chip level. So,
Mark, I know Intel is working in this area.
Well, we have a silicon photonics group for communication, you know, obviously. So anytime you want to communicate a lot of data over, you know, meters, tens of meters or more, optics is a good way to go. But using optics for computing, I just don't see it. The dimensions are too large because the wavelengths are large. The amount of energy it takes to convert photons to electrons and back again is excessive, so I just don't see that happening.
Several questions that the audience have provided are on the theme of security. So how does, from what we've talked about in terms of the underlying microelectronics technology, the architecture, some of these hybrid approaches, how do those speak to concerns about security?
So I'll say something controversial because we're late in the evening.
And then we'll end.
It's embarrassing where we're at in regards to security. You know, I've think at DEF CON, they just demonstrated an 11-year-old just attacked a critically important system. And it's pretty amazing that we could go this far with performance and like not nearly as far enough as we need in performance in security. So we need to be able to do performance, cost, and security simultaneously. And I think the chip is really a great place to look, right? Because the software is so dynamic and it's so easy to get different, functional blocks from so many different locations. The chip itself is a much more tangible, locked-in capability. I think over time, what you will find is the chip plays a much more foundational role in the security stack. And I actually think one of the things that will shift some of the discussion from sort of the software versions of the world to a more chip-centric version of the world. On the other hand, it's also going to be the thing that really confuses what the performance vector is. If every time you're going to try to get a performance vector, you have to think of what the unknown threat space is, right? Which is what cyber is all about, is trying to predict the unknown threat space. If you knew about it and you didn't take care of it, that's on you. But that, unfortunately, it's the thing that someone hasn't thought of yet that's actually going to attack you. And that is a very difficult space to design into.
Mark, do you have any thoughts?
Again, I'm not an expert in the area of security, but it seems like our desire to place electronics everywhere, create Internet of Thing devices, is outstripping our ability to make them secure. And again, from my somewhat amateurish point of view, security seems like a tax that we're not quite willing to pay. Other features you have to add to the software or to the hardware to make it secure that initially you don't want to add, don't think of adding, but we have to do it.
Yeah.
I'm sorry that this is approaching a little bit of a pop quiz, this barrage of questions, but this will be the last one, but I think it is an important one because it's something that people, if they're like me, have heard about but not really grasped. And this is this idea that we can address kind of what's happening with scaling by going into the third dimension. And we hear this especially in terms of things like flash memory, where they are some huge number of stacks. And could you just briefly help us understand this, what we should make of this kind of move to the third dimension in terms of chips?
I'm a fan of that. I think that is what we need to do more of. Now, it may not completely address some of the goals of Moore's Law in terms of making each device cheaper. If you're stacking them, maybe you're not making them cheaper. But it's also, again, maybe my analogy is getting tired, but the human brain works so well because it has a very dense three-dimensional connection of interconnects. We don't have that in electronics, nothing equivalent to that in electronics today.
I think it's a great vector. I think it's hard as can be. There's many different plays to this. You can do things separately and bond them together. That has been around for a long time. DARPA had a program in the late 80s doing that. It kind of works. It didn't really pay off. What we're doing now is growing low temperature devices on top of a silicon base. I showed the carbon nanotubes and ReRAM. There's more approaches you can do than just that, but that's really what Stanford and MIT are doing for us. The numbers are amazing, right? We can't yield that. It's really, really hard, so it's not a good idea yet. But if you look at the simulation numbers on what an algorithm looks like when it's running inside of that really co-located memory and processing stack, it's off the charts, and we're on a path to see if it will yield, and I think we'll know in the next 3 to 4 years.
Well, thank you very much. To close, I'll ask the audience to help me with 3 things. First and foremost, why don't you join me in thanking Bill and Mark? Thank you. I'd also like your help with thanking our generous sponsor for this evening's event, Lam Research. And on a personal note, I just wanted to say that this is the last live event I will get to enjoy working with 2 great producers of our live events, Chanel Lauren and Lauren Miyamoto, who brought us tonight's event. So help me thank them for a wonderful series of events. Thank you all very much.